you know, having understood the basic tenets of electrostats, electric field, etc., and how charges respond, we move on to another issue related to charges, which is about flow of charges and the associated dynamics. So, if we have a point A, which is at a higher potential compared to a point B, and I join A to B with a conductor. A at a higher potential, B at a lower potential, and I join A and B with a conductor. What happens is positive charges flow from A to B till such time that the potentials get equalized, right? They would be positive charges flowing from A to B till such time that the potentials get equalized, right? Now, if there was a mechanism that could maintain the potential difference between A and B, if there was a mechanism that could maintain the potential difference between A and B, one thing in common parlance, if A is at a higher potential compared to B, then we say A plus B minus. This is what it means. That means potential of A higher compared to potential of B. This is what it means. Now, if there was a mechanism that could maintain the potential difference between A and B, then there would be a continuous flow of charges from A to B. There would be a continuous flow of charges from A to B. And that flow of charges from A to B is designated by current I, which is rate of change of charge, rate of change of flow of charge with time. Rate of flow of charge with time, that's the current flowing through this element AB. Now, say the mechanism that maintains the potential difference between A and B is this: A maintained at a higher potential and B maintained at a lower potential. This mechanism which does that, is called a battery or a cell. It's called a cell. A collection of cells is a battery essentially, but the mechanism that maintains the potential difference between A and B is called a cell. It's called a cell. Now, if V is the potential difference maintained between A and B, what really happens is there is an electric field that is set up from A to B. Inside this conductor, there is an electric field that is set up from A to B. That electric field drives positive charges, from A to B. When a positive charge starts at A and it flows past the conductor and it comes to B, then it would have lost potential energy. It would have gone from higher potential to lower potential, right? When it comes to B, when that positive charge arrives at B, this mechanism produces an electric field in this direction. From positive terminal to negative terminal, it produces an electric field. Now, in order that the positive charge could move from B to A, there would have to be some work done against this electric field. Very clearly, when the charge has to be transported from B to A, it would have to be energized, because it would have to move from a region of lower potential to a region of higher potential. So it would have to get energized. Where would this energy come from? This would come from this mechanism, the cell. This would come out of this mechanism, the cell. We would not bother about, what exactly happens inside the cell, but very briefly, the energy required for the charge to go from B to A comes from this mechanism, the cell. Now, once it comes to A, it gets energized, then it's ready to take up this loop again. And the same loop gets executed again and again, resulting in a current, which is rate of flow of charge with time, right? Now, if this is a conductor in which the current flowing through this conductor is proportional to the potential difference applied across its ends. See, V is the potential difference applied across the ends of this conductor. Then, if I is found to be proportional to V, that means if you double the V, the I gets doubled for this conductor, then this conductor is referred to as an ohmic conductor. This conductor is then referred to as an ohmic conductor. The constant of proportionality between I and V is called the resistance R of the conductor. This is the constant of proportionality between V and I, and it's referred to as the resistance R of the conductor. It's called the resistance R of the conductor. And it's measured, as you already know, in SI units, ohms. Now, again, it has been empirically established that if there is a conductor, if this is a conductor of length L and area of cross section A, and if area of cross section A, then the resistance of this conductor can be obtained by rho L by A, where L is the length, A is the area of cross section, rho is a property of the material of which the conductor is made, and is called specific resistance or resistivity. Is called specific resistance or resistivity of the material of which. So this is a property of the material. L and A are geometric factors. L and A are geometric factors. Now, right? Theoretically, the cell that I'm talking of, the battery that I'm talking of, has terminals A and B. Say positive terminal A and negative terminal B. And in a state where there is no current flowing in the circuit, the potential difference between A and B is called the EMF of the cell. In a state when there is no current flowing in the circuit, the potential difference between A and B is called the EMF epsa of the cell. The potential difference between A and B in absence of current. Now, what happens if there is current? What really happens is, when current flows from B to A, when charges flow from B to A, this mechanism offers some resistance. There is resistance which is called the internal resistance of the cell, which is referred to as the internal resistance of the cell. So, when there is a current flowing through the cell, then say this is the cell, and there is some resistance that this mechanism offers R, which is called the internal resistance of the cell. It will have no role to play when there is no current. It will have no role to play when there is no current. But when there is a current, I, then between A and B, the drop will no longer be epsa. The drop will no longer be epsa. If the current I is flowing like this, then across the terminals, so this arrangement could be replaced by an arrangement of this kind, where let's say A comes here and B goes there, and B goes there. If there is a current flowing through this arrangement, if there is a current I flowing through this arrangement, from negative to positive, essentially, this entire arrangement could be replaced by, let's say, terminals which offer no resistance, along with a resistance, they could be placed side by side. Then the resistance consumes part of epsa. The resistance consumes an amount, I times small r is consumed by resistance. So what's available to the rest of the circuit is no longer epsa, but what's available to the rest of the circuit is epsa minus IR. Epsa minus IR is what is available to the rest. Yeah. All that I'm saying is, epsa is the EMF of the cell, which is the potential difference between its terminals when there is no current flowing through the cell. Theoretically, it's okay to assume that there is no resistance, but realistically, while current flows from the terminal B to A or from A to B, there is resistance offered by the cell. This resistance offered by the cell is called internal resistance, small r. So this entire arrangement between A and B could be replaced by a battery, epsa, along with a resistance, small r, where if there is no current flowing, then the potential difference between A and B would have been epsa. But now, because of a current flowing through this, the part of epsa is consumed by this resistance. IR is the potential that is hogged up by the resistance, and what's available to the rest of the circuit is what is available across A and B, which is epsa minus IR, right? So which means, so this is a real battery, and an ideal battery is one in which small r is 0. That's an ideal battery, right? So they would tell you whether you're going to deal with a real battery or an ideal battery. In an ideal battery, whether or not there is a current, the drop across the terminals will be the EMF of the battery. But in the event there is a current, the drop that is available across the terminals will be different from the EMF of the battery. Clear? Now, say this is a battery, epsa, with internal resistance R, and is connected to an external resistance capital R. This arrangement results in a flow of current I. This arrangement results in a flow of current I through the loop. Then across a resistance R, if a current flows, then in the direction of the current, potential drops by an amount IR. Potential drops by an amount IR. So the potential here drops by an amount IR. Across capital R, potential drops by an amount IR. and then current comes here. Then there is again drop of potential across the small r. So the drop across the small r is I times small r, right? And then when I go from terminal B to A, the drop is minus epsa because there is an increase of potential. So the drop is minus epsa. This is the drop across capital R. This is the drop across small r. From B to A, the drop is minus epsa because from B to A there is an increase in potential by an amount epsa. So the drop will be minus epsa. The drop will be minus epsa. So now, in the process, what you have done is you have started from A and you have come back to A. This is the sum of the drops from A to A. This is a closed loop. Electric field is a conservative force field. In a closed loop, the algebraic sum of the drops, potential drops, must be 0, right? When you are starting from A and coming back to A, then there is a drop across this, there is a drop across this, there is a drop across this, there are drops across various elements. But because of the conservative nature of the field, the algebraic sum of these drops in starting from A and coming back to A must be 0. So algebraic sum of these drops must be equal to 0. The algebraic sum of the potential drops in a closed loop must always be 0, and this essentially is what's called Kirchhoff's voltage law. This is called Kirchhoff's voltage law. Or KVL. Kirchhoff's voltage law or KVL. Let's build it up. I'm going to look at all those variations. Let's go from scratch and build it up, right? Let's not jump to things so right away. So that's Kirchhoff's voltage law. Algebraic sum of the drops, potential drops in a closed loop, is going to be 0. So we'll take drops. So all drops positive, all increase would be negative, right? Now, again, in a complicated network, there could be a junction J. A junction J. And there could be current entering the junction from some place. There could be current leaving the junction. Some currents are entering the junction J, some currents are leaving the junction J. But there is no accumulation of charge under steady state conditions. So if there is no accumulation of charge under steady state conditions at any point, that means eventually all the current that is coming in must be equal to the current that is leaving the junction, right? All the current coming in must be equal to current leaving. That means algebraic sum of the currents at the junction J must be 0. That means if I take all that is coming in as positive and all that is leaving as negative, then the algebraic sum of these i's must be 0. That means we must have, say, I1 minus I2 plus I3 plus I4 is 0. Algebraic sum of the currents entering a junction must be 0, right? And this, see, I1 coming in, I2 leaving, I3 coming in, I4 coming in. This is the algebraic sum of the currents associated with the junction J. Either I can take all that is coming in as positive and leaving negative, or vice versa. That does not matter, right? Essentially the statement is current that is entering must be equal to current that is leaving. See, all the current that is entering is I1 plus I3 plus I4 is the current that is entering, equals I2 is the current that is leaving. That's simply a continuity requirement for flow of charge. No charge is getting accumulated, so all the charge that is coming into a junction must necessarily leave that junction, right? So this principle is called Kirchhoff's current law. means there is no accumulation of charge. Everything that is coming in is leaving. That is steady state. Kirchhoff's current law, KCL. Right? No, charge is not zero at that point. Charge is in a state of motion. There is charge, but all the charge coming in is equal to charge leaving. The conductor at across any cross section is electrically neutral that way. That's all that can be said. Yeah, charge conservation. This is simply charge conservation. This is just a restatement of charge conservation, right? Now, say if I have an ideal battery EPSA 1 equal to 2 volts, a resistance say R1 equal to 2 ohms, another battery EPSA 1 equal to 1 volt, ideal battery say, and a resistance R2 equal to 3 ohms, and say there is another loop R3 equal to 4 ohms, there is a battery say EPSA 1, so let me call it EPSA 2, EPSA 3 equal to 5 volts, and say R4 equal to, let me have another resistance here, small r equal to 2 ohms and R4 equal to 5 ohms say. Something like this. Suppose we have a network of resistors as shown. I want to be able to find the current through various branches of these two loops. Various branches of these two loops, I want to be able to find the current. Now what I do is, say I start with a current I1 through this. I1. This current I1 comes to this junction J and it gets bifurcated, right? Part of this current goes through this, say I2, and then the rest goes through this, which is I1 minus I2 goes through this, and it circulates in this loop, right? Essentially there are two unknowns, I1 and I2, and if I can eventually apply KVL to this loop and KVL to this loop, I'll be able to solve for I1 and I2. One more thing, when I2 comes here and then I1 minus I2 comes here, they merge together and they produce I1, and I1 leaves this. So all currents are now balanced. All the junctions are in a balanced state, with this diagram, right? Now let me apply KVL to this loop, right? So let me call it loop 1. Let me call this loop 2. Drop across this resistance is what? I1 into 2. I1 into 2 is the drop across this resistance. I1 into 2. Then I2 into small r, that means I2 into 2 is the drop across this resistance, right? From here to here there is a drop by 1 volt. So all drop positive. So plus 1. Then I1 into 3 is the drop across this. And then from here to here there is an increase. So minus 2 equal to 0. Equal to 0. That's KVL applied to loop 1. That's KVL applied to loop 1. Let me apply KVL to loop 2. Let me apply KVL to loop 2. I1 minus I2 is the current flowing in this branch. So drop across this resistance is going to be I1 minus I2 into R3, right? R3, which is 4 ohms, right? From here to here there is an increase. So minus 5. And then the drop across this is I1 minus I2 into 5. Yes or no? And then go this way. Go this way. From here to here, see, I'm circulating this loop like this. From here to here there is an increase. 1 volt. So minus 1. Minus 1. And then I2 like this is like minus I2 like this. I2 this way is the same as saying minus I2 like this. So the drop here is going to be minus I2 into small r. The drop here is going to be minus I2 into small r. So, and this must be 0. That's KVL applied to loop 2. That's KVL applied to loop 2. Yes or no? You can solve these two equations and obtain the currents in various branches. You can solve for I1 and I2, simple simultaneous equations, and you would know the current in all branches of the two loops associated, right? So essentially all that we have done is we've applied KVL and we have made sure that at all the junctions the currents are balanced. This is all that we have done, right? Now, sometimes there could be multiple loops. Sometimes there could be multiple loops. Say, suppose there are multiple loops like this. Let me refer to these resistors as R1, R2, R3, R4, R5, 6, R7. Now, what we could do is the following. I could have started with a current I1 flowing through this battery. I could have started with a current I1 flowing through this battery. This I1 comes to this junction. It gets bifurcated into two. There is I2 going here, and say there is I1 minus I2 going here, right? This I1 minus I2 comes to this junction, and say I3 goes here, and I1 minus I2 minus I3 goes there, right? And this I1 minus I2 minus I3 comes down here, I1 minus I2 minus I3. See, this is R7. It merges with this I3, giving me I1 minus I2 going this way. And then this merges with I2, I1 minus I2 merges with I2, giving me I1 going this way. All currents are balanced, right? I could apply then KVL to this loop, I could apply KVL to this loop, I could apply KVL to this loop. Three unknowns, I1, I2, I3, and we could solve for them, right? So here we have deployed KVL and KCL. KCL to all the junctions to make sure that the currents are balanced, KVL to all the loops. That's essentially a conservation principle, right? Now, an alternative to this is what I'm going to suggest. This is not, if there were two loops, you know, I would have done what we did. But this is not what I'm going to do if there are more than two loops. It'll work, this will work. But what I would do is what's referred to as the Maxwell's loop rule. I'll apply Maxwell's loop rule. In fact, that will just avoid so much of clutter and the headache of balancing currents at various junctions. See, I could have added a fourth loop, and the headache of balancing currents at various junctions would all be ours. To avoid all that, we use what's called the Maxwell's loop rule. What I assume is a current for every loop. There are three loops. What I'll assume is, I will assume a current for every loop. Say I1 like this for this loop. For this, I2. For this loop, 3. I would assume currents for every loop. This I2, let me remove just this I2 that I'm talking of, right? I1 through this loop, I2 through this loop, and I3 through this loop. Currents through the three loops. Okay. And now with these loop currents, these are loop currents. I'm applying loop currents so that I don't have to bother about junctions. And you'll see how I will not have to bother about junctions when I assume loop currents like this, I1, I2, I3. When I apply KVL to this loop now. When I apply KVL to this loop. Okay, you can start anywhere from here to here. There is a drop, so epsa 1. I'm applying KVL to this loop, loop 1 say, epsa 1. And then I1 into R2 is the drop across this. Now, look at R3. R3 is like a I1 going this way because of this, and I2 going this way because of this. Yes or no? This loop drives I2 upwards, and this loop drives I1 downwards. So the net current through R3 is going to be I1 minus I2. I1 minus I2. So I1 minus I2 into R3 is the drop across this. Right? And then I go from here to here. There is an increase. So minus epsa 4? Minus epsa 4, yes or no? Right? And then I go this way. I1 into R1 is the drop across this. Algebraic sum of these drops must be 0. That's KVL applied to this loop. Yes or no? Right? Now let me apply KVL to loop 2. Let me apply KVL to loop 2. Can I wipe this off? Have you made a note of this? I'll explain again. All that I did was there were three loops, and with each loop I associated a loop current I1, I2 and I3. Okay. From here to here, what's the drop? Epsa 1. I1 into R2. Drop across this. Now drop across this. Hello. I1 is the current flowing because of this loop current, and I2 is the current flowing up because of this loop current. So what's the net current through this? I1 minus I2 downward. So I1 minus I2 into R3 is the drop from here to here. Yes or no? and then minus epsilon 4, and then I1 into R1. All of this must add up to 0. Do you understand this now? No confusion? Right? KVL applied to loop 1. Can I wipe this off? Let me apply KVL to loop 2. KVL applied to this loop now. Now from here to here there is an increase. So minus epsilon 2. Then I2 into R4 is the drop. Right? And then from here to here, realize I2 going this way and I3 going this way is like a I2 minus I3 going this way. Yes or no? So plus I2 minus I3 over R6, dropping this much? Yes or no? And then I2 into R5 is a drop across this. And then it's as if there is I2 going up and I1 coming down is like a I2 minus I1 going up. Is like a I2 minus I1 going up. So plus I2 minus I1 R3. And all of this must add up to 0. That's KVL applied to loop 2. Right? Let me move to loop 3. Let me move to loop 3. Can I wipe this off if you're done? Yeah, I'll wait. Of course, yes. No, which means now if you have to find the current through, if you have solved for I1 and I2, the current would be I1 minus I2 like this. The current through this would be, through this branch is going to be I1 minus I2. Now you will superimpose currents in branches in which there are multiple currents associated. Right? Say for example in this branch, there is I1 going this way and there is I2 going this way. Suppose I1 turns out to be greater than I2 when you solve. Then you will find, suppose I1 turns out to be, 5 amps and I2 turns out to be 3 amps. That means there must be 2 amps going this way. But suppose I2 turns out to be bigger than I1, then the net current flowing through R3 would be I2 minus I1 upwards. It'll all match. It'll all match. There is no inconsistency in this. Right? Let me apply KVL to this loop finally. Right? This loop 3. I3 into R7. Right? Then from here to here there is an increase. Minus epsilon 3. Oh, let me put as R8. This is R7, so R8. And then drop across this is I3 into R8. And then look at this branch. There is I2 going this way, there is I3 going this way. That means there is a I3 minus I2 going upwards, right? Into drop R. This must be 0. That's KVL applied to loop 3. 3 equations, 3 unknowns. You can solve for I1, I2 and I3. But the only advantage in merit in doing this is that you don't have the headache of balancing currents at every junction. That's a merit in doing this. Clear? Of course, in case there are only 2 loops, then you don't bother too much about all this. Either do this or even balance junction at 1 or 2 points is not an issue. But if there are multiple number of loops, theoretically circuits could be like 20-30 loops. And so imagine the number of junctions that it could have produced. And then balancing currents at every junction would be a problem by itself. And you don't want to deal with it. Then this Maxwell's loop rule comes in very handy. Right? Now, in an electrical circuit, the whole idea is to obtain energy across a load. To obtain energy across a load, if there is, the load could be in the form of a motor, for example. If there is a current flowing through the motor, there would be mechanical motion obtained. There would be power available across the motor in the form of mechanical energy when a current is driven through the motor. If there is a resistance, which could be like a heating coil, for example, right? If a current is driven through the heating coil, then the power obtained out of this is in the form of what's called joule heating. Joule heating. So depending on the load, there is power associated with the load when there is a current driven through the load. The load could be anything. It could just be a resistance, or it could be a motor, or it could be some other device. One way or the other, does not matter, right? So let's say part of a bigger circuit, and there is a certain load. There is a certain load. This is just part of a bigger circuit. And there is a current I driven through this. In the direction of the current, potential will drop. In the direction of the current, the potential will drop. Say the potential drops by an amount V when a current I flows through this load. Potential drops by an amount V when a current I is driven through the load. Now in a small time dt, let's say a charge dq flows from this end to the other end, right? Then the energy lost by that charge in flowing from this end to that end is going to be the potential through which it drops into dq. That's the energy lost by the charge when it goes from, when a charge dq goes from higher potential to lower potential, it loses energy. This is the energy that it loses, right? The value of the charge into the potential through which it drops. That's the energy lost by that charge, right? That energy is available to the load. This energy is available to the load. This is the work done for the load. This is the work done for the load. This is the energy available to the load when this charge dq flows past the load, right? This is the work output, so to say, of this flow. This is the work output of this, right? This is why a current is being driven, because we want this dW. It could be in the form of heat, or it could be in the form of, let's say, mechanical motion of the motor, one way or the other. This is the output. This is the energy output. And let's say the rate at which energy is available to the load is dW dt. That will give me the power associated with the load. That will give me the power consumed by the load. That will give me the power consumed by the load. The power P consumed by the load is going to be dW dt, which is V dQ dt. These many watts will be available across the load, but dQ dt is I, the current I. So this is going to be V I, right? So no matter what the load is, the power consumed by the load would be the current flowing through the load into the potential difference across the load. That will be the power consumed by the load. That is the power made available to the load, these many watts. Okay. Load is in the form of a resistance. If the load is in the form of a resistance and a current I flows through this, resulting in a drop of V volts, then the power associated with this is going to be V into I. And this would be available as what is referred to as joule heating. This would be referred to as what's called joule heating. V into I, where V could be written as IR. V could be written as IR. So this is like a I square R, which is the joule heating of the load, which is the joule heating of the resistance. the charges, when it flow from here to here, they collide with the molecules, resulting in this dissipation of heat. So this is the typical joule heating that is available across a resistance, the I squared R, right? Which could also be written as, see, I could written I as V by R. So this could also be written as V squared by R. Right? Now, say there is a load R and it's connected to a battery with EMF epsa and with small r as the internal resistance. So the battery could be replaced by an ideal battery in series with a internal resistance small r. Epsa is the EMF of the battery. Internal resistance of the battery. And you can't do much about this. But let's say at different times you are connecting different loads across, say, these 2 points. These are 2 points, A and B. This is like a socket across which you can connect a load. You know, what is that? That's actually a socket. You could connect different loads across this. You know, these plug points, they are sockets. These are points, A and B, across which you could connect a load. You could connect a fan across this. You could connect a bulb across that. You could connect a torch across that, whatever, right? So, this load could be varied. You don't have a circuit with a fixed load. I mean, you just provide points A and B across which various loads could be connected. Yes or no? Now, realize that if I is the current driven through this, then I can apply KVL to the loop and obtain the value of I, right? So the drop across this, drop across the resistance is going to be I into R. And then there is a drop across this small r, I into small r. And then from here to here there is an increase, so minus epsa. All of this must add up to 0. Right? So I then turns out to be epsa divided by r plus small r. Right? Now, the power associated with this load would be I squared into capital R is going to be the power associated with this load, right? This is my load. Let's say L, power associated with the load. Is going to be I squared into R. I squared into R is going to be the power associated with the load. These many watts would be consumed by this load, right? Where I we have obtained as epsa by R plus small r whole squared. Yes or no? Very clearly, if you vary the load, then the power would be different for different values of the load. We want to be able to plot the characteristic of the power versus the load resistance R. Power versus the load resistance R. Now, One thing that you can see from here is, so this is the power across the load, PL, epsilon squared divided by, on dividing by R plus 2R plus R by R squared by capital R. This is what you get. Do you realize that? See, this will be capital R squared divided by R will give me this. The middle term 2RR divided by capital R will give me this. And then R squared divided by capital R. Right? Very clearly, when capital R is 0, the load across is 0. Right? When capital R is 0, load will be 0. Right? When capital R tends to infinity, this will tend to 0 and this will tend to infinity. So this will tend to 0. Right? So when capital R tends to infinity, the power across the load will again tend to 0. Yes or no? I'll repeat, kya?
So the R, there's one R above and there's one R in the denominator.
So when capital R tends to infinity, this will tend to 0 and this will tend to infinity. So this whole thing will tend to infinity and this ratio will tend to 0, isn't it? Which means now realize that the power across the load versus the load resistance R, it's 0 here, and as R tends to infinity, this is again 0, which means you would expect a maximum load to occur somewhere. This is what you would expect. For a certain value of capital R, there would be a maximum load obtained somewhere. Yes or no? It starts from 0 and it goes to 0. That means it must have attained a maximum somewhere. It must have attained a maximum somewhere. Now, do you realize PL would be maximum when R plus 2R plus R squared capital R is a maximum? I'm sorry, is a minimum? Is a minimum? Right? Now 2R anyways is a constant. That's the battery character. Right? This would happen when R plus R squared by capital R is a minimum. Right? Hey, R plus R squared by R, the arithmetic mean of this is greater than or equal to the geometric mean. That means root R into R squared by capital R. AM greater than or equal to GM. Right? Which means R plus R squared by R will be greater than or equal to 2R. That means what's the minimum value of this expression? 2R. The minimum value of this is 2R. R assumes a minimum equal to 2R. The minimum value of this expression is 2R. So which means power would be maximum when R plus R squared by capital R becomes equal to 2R. And when would this become equal to 2R? When AM becomes equal to GM? When would this become equal to 2R? When AM becomes equal to GM. And when would AM be equal to GM? When the quantities are equal, right? So PL will be maximum when R plus R squared by capital R becomes equal to R squared by capital R. That's when AM will become equal to GM when the quantities involved are equal. When capital R becomes equal to R squared by capital R. That means when capital R becomes equal to small r. When capital R becomes equal to small r. That means when the load resistance becomes equal to the internal resistance of the battery, when the load resistance becomes equal to the internal resistance of the battery, the power dissipated across the load will be a maximum. Yes or no? We could differentiate this. Now you have learned calculus, you could differentiate and find the minimum value of this. Or you could express this as a perfect square plus some constant then also, either way, right? So when load resistance becomes equal to the internal resistance of the battery, load resistance becomes equal to the internal resistance of the battery, the power across the load is a maximum. That means when capital R becomes equal to small r, PL will become a maximum. And what's the maximum PL? What's the maximum PL? It will be 4R. See, R plus R squared by capital R becomes equal to 2R plus 2R. So that makes it 4R. So then this becomes, this was all epsilon squared. I just missed out on the epsilon squared. This was all epsilon squared. Epsilon squared maximum equal to epsilon squared by 4R. Epsilon squared by 4R is the maximum load that could be dissipated across the, and that happens when the load resistance matches the internal resistance of the battery. This is a very commonly used result. Even though it's such a simple result, it will be actually looked upon as a very sophisticated result. You will find that it's really versatile in very complicated situation. If you use this, it'll do wonders for you. We'll see that in problem solving though, right? Now, there are times when you talk of an equivalent resistance. Between 2 points, there could be a maze of resistors. Between 2 points, there could be a maze of resistors, a network of resistors between 2 points. Say there is a point A and there is a point B. Between these 2 points, there is a black box, which is a network of resistors. And this network of resistors you want to replace by a single resistance. That means you want this to be equivalent to a single resistance between A and B. In a manner, these two would be looked upon as equivalent if whatever be the network of resistors here, these are the ends across which the network is connected. If I imagine a battery, hypothetical battery of V volts to be connected between, if I imagine a battery of V volts to be connected between the ends A and B of this network, and if it results in a current I, hypothetical battery of V volts connected across A and B, and if it results in a current I flowing through the battery, it's a current I flowing through the battery, then if this has to be equivalent to this, then what it means is that the same battery between the ends of this equivalent resistance would result in the same current I flowing through the battery. This V is arbitrary. This could be any battery connected across the network of resistors. And if we find that a current I flows through this, and the same battery when connected across this results in the same current I, then we can conclude that this must be an equivalent resistance of this network of resistors. This network of resistors could be replaced by one single resistance, R equivalent. This is what is meant by equivalent resistance across 2 points. We have to talk of 2 points. Which 2 points? There could be a collection of resistors and there could be many points. So it's not like just given a collection of resistors, you'll say, what's the equivalent resistance? You will have to specify across which 2 points of that collection am I seeking the resistance, in the sense that, you know, I could have had, say, a collection of resistors like this, right? I could seek equivalent resistance across A and B, in which case the hypothetical battery would have to be connected across A and B. Or I could seek equivalent resistance across C and D. Say C and D are these points. Then I would have to imagine a battery connected across C and D. So it would have to be specified. Equivalent resistance across which 2 points would have to be specified and stipulated, right? Now, the most simplest collection of the simplest network of resistors are resistors in series and resistors in parallel. Those are the simplest possible network of resistors. Say, if I talk of resistors in series, say connected between points A and resistance R1, and there is a resistance R2. These two resistors are connected across points A and B. And I want to find the equivalent resistance across A and B. Then all that I would do is I would imagine a battery of V volts to be connected across these, right? They are said to be in series if the same current flows across them. If the same current flows across them, then they are said to be in series. This is equivalent to a single resistance connected between A and B. When the same V volts is applied, the same current I must flow. The same current I must flow, right? So now, very clearly, if I apply KVL to this loop, then I get I into R1 plus R2 minus V equal to 0. Drop across this, minus V increase, that must be 0. Yes or no? So V must be I into R1 plus R2, right? Now if I apply KVL to this loop, then this will give me I into R, drop across this, minus V equal to 0. So V then turns out to be I R equivalent, say R equivalent. V then turns out to be I R equivalent. Then on comparing these two equations, you clearly find that R equivalent is R1 plus R2. So if you have resistors in series, they can be replaced by a single resistance, which would be the sum of the resistors. And whenever I say resistors are in series, it's about connected in a manner that the same current flows through them. That's when they are said to be in series, right? I mean, you've been doing this ever since class 6, right? 9 and 10. Right. I still want to reiterate this because when I take up complicated meshes and networks, you realize what the idea is. The same idea is going to be deployed. That's why I'm deliberately doing this. Say, resistors in parallel. Say R2, and across these 2 points A and B, they are in parallel. Now one thing, From now on, what we'll do is, instead of drawing a full loop like this, saying that there is a battery connected of V volts, instead of doing this, what we'll do is that will save us some time. That is also conventional. Say this is V volts. Instead of drawing all of this, what we'll do is we'll simply do a plus here and a minus here, means A connected to the positive terminal of a battery, B connected to the negative terminal of a battery. Eventually there is a full loop from A to B, right? But this is what we'll do. Instead of drawing the battery every time, we'll do a plus minus, means A and B are connected to terminals of a battery. And let's say V volts. Clear? That means potential drop from A to B would be V volts. Potential drop from A to B would be V volts. Now, this would be looked upon as equivalent across A and B. This is A, this is B, this is R equivalent. If I apply the same potential difference V between A and B, potential difference from A to B is V volts. And if it results in a current I here, then the same V volts across A and B, when applied here, results in the same current I. That's when these two are looked upon as equivalent, right? Now, look at this. There is a current I coming from the battery. At this point, it gets bifurcated. This is I1 and it goes as I2 here, right? Now, R1 is connected to the same terminals of the battery. R2 is also connected to the same terminals of the battery, right? So, the drop across R1 must be the same as drop across R2 must be equal to V. Yes or no? Right? So, can I say that this V must be the drop across R1, which is I1 R1, must be the same as drop across R2, which must be I2 R2, where I1 plus I2 must be the total current flowing through the battery. See, Siddhant, this is the circuit essentially. This point A, this terminal A of the battery, this terminal B of the battery. Electrically, all these points are A's. So this is A. Electrically, all these points are B's. So this point is B. So electrically, this resistance is connected between 2 points, electrical points A and B. This resistance is also connected across the same set pair of electrical points A and B. So the drop across this resistance is the same as drop across this resistance, which is the drop from A to B. Now, if the drop across this is V, that means now from A to B the drop is V, which is like I into R equivalent must be V. So, I into R equivalent must be, right? So, as you can see, I1 plus I2 from this equation, I, which is total current, which is I1 plus I2, I, which is I1 plus I2, I1 is V by R1, I2 is V by R2. So, V into 1 by R1 plus 1 by R2? Yes or no? I1 plus I2 is V by R1 plus V by R2, which is the total current I flowing through the battery, and I is also V by R equivalent. I is also V by R equivalent. This I is V by R equivalent. So that will give me equivalent resistance 1 by R equivalent as 1 by R1 plus 1 by R2. Hey, one thing, resistors in parallel or in series is not about how they are geometrically connected, in the sense that, if there is a resistance like this, then there is a resistance like this, and there is a resistance like this between A and B. Don't think that they are in parallel just because they look like being in parallel, right? So just a safeguard that I'm assuming, right? They are in series from A to B. They are not in parallel, right? They look parallel geometrically. So if there were n resistances in parallel, then 1 by R equivalent would be 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by Rn. You knew all of this, right? Now, say there could be a more complicated network. There could be a more complicated. It's not like in a network you'll have resistors in series or in parallel or just a combination of the two. If it's series and or parallel, then it's simple. You've already dealt with those things umpteen number of times. But there could be a network in which you cannot reduce it to a series parallel combination, right? Then you will have to go from first principles, like I said, and obtain the equivalent resistance. I'll also teach you some proper tools that will make life a little simpler. But let me go from first principles and then teach you some sophistication there. A simple tool, let's say a more complicated collection of resistors which cannot be reduced to a series parallel combination. How do I find equivalent resistance in such a situation? Okay. Say this is 1 ohm, 2 ohms, 3 ohms, 4 ohms, 5 ohms. Something like this. First of all, I would have to know across which 2 points I am seeking the resistance. I would need to know across which 2 points I am seeking the resistance of this network. Say between points A and B here, I am seeking the equivalent resistance. That means between A and B, I want to replace this network by a single resistance. That means, when I say I'm seeking resistance between A and B, that means I'm seeking to connect a battery across those 2 points. When I'm seeking resistance across those 2 points, that means I'm seeking to connect a battery across. That means one of the points connected to the positive terminal of the battery, the other one connected to the negative terminal of the battery. Now, what I do is, like I told you, I imagine a battery, say V volts. I imagine a hypothetical battery which is V volts between points A and B, where I'm seeking the equivalent resistance. Okay. And if this hypothetical battery of V volts results in a current I flowing through the battery, then the equivalent resistance across A and B is going to be V by I. Then the equivalent resistance, that means between A and B, it's like, this is the equivalent resistance between A and B. That means, say if this is the battery connected, and if there is a current I that results with this, with the same volts applied across A and B, then the R equivalent is going to be V by I. V by I is going to be the R equivalent across A and B. So in this case, I want to find the ratio V by I. I want to find the ratio V by I, and that's going to be the equivalent resistance between points A and B. V by I, V, the hypothetical battery connected, and if I is the current flowing through the battery when connected between A and B, then V by I is going to be the equivalent resistance across A and B. Clear? Now, Say this I breaks down into I1 and I2. Breaks down into I1 and I2. This I comes to this point and breaks down into I1 and I2. This I1 goes here, comes to this junction, right? And say I3 goes here and I1 minus I3 flows down to this balance of current in this junction. Yes or no? I1 coming here, I3 leaving, so I1 minus I3 going in here, right? So I1 minus I3 coming in here, I2 coming in here. What's the total current coming in? I1 plus I2 minus I3, and that must be the total current leaving. That means I1 plus I2 minus I3 is the current which is leaving. Now I3 comes here, I1 plus I2 minus I3 comes here. So what leaves us? I1 plus I2. All currents balanced now. All currents balanced. Isn't it? I1 minus I3 coming here, I1 plus I2 minus I3 coming here. So I1 plus I2 leaving. Yes or no? Yes, and I1 plus I2 was actually I. This I was actually I1 plus I2. So do you realize all junctions are balanced? KCL. Now I can apply KVL to this loop. I can apply KVL to this loop. Right? Say if I apply KVL to this loop, then I get I1 into 1, right? Plus I1 minus I3 into 2 and then I2 this way is like minus I2 this way, so minus I2 into 3, that must be 0. That's KVL applied to one loop. Yes or no? Now let me apply KVL to this loop. I3 into 4. Then I1 plus I2 minus I3 going this way is like minus of I1 plus I2 minus I3 going this way. Into 5. And then I1 minus I3 going this way is like a I1 minus of I1 minus I3 going this way. That must be 0. Yes or no? Right? Now what I am seeking is the equivalent resistance across A and B is V divided by I. V divided by I. Right? Now to obtain V in terms of these currents, for example, what could I do? V is the potential difference from A to B. I can see the potential difference between any 2 points in an electric field, no matter how you go from A to B, is going to be the same. You could go from A to B like this, or you could go from A to B like this, 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 come to B. Then also, no matter how you go from A to B, it's path independent. The potential difference is going to be the same, right? So one way to obtain the potential difference from A to B, which is V volts. V volts is the potential difference between A and B. I could go this way. I1 into 1 plus I3 into 4 is the potential difference between A and B. The drop from A to B is going to be I1 into 1 plus I3 into 4, right? So the potential difference from A to B is going to be I1 into 1 plus I3 into 4, right? Yes or no? Now realize that both, if you look at these two equations, can I solve for I1 and I2 in terms of I3? Yes. I can solve for I1 and I2 in terms of I3, right? So I1 and I2 are known in terms of I3. So I1, for example, will turn out to be some constant into I3, right? Look at this V. RAB is V, which is the drop, I1 into 1 plus I3 into 4. Divided by I. I is I1 plus I2. Yes or no? Clear? Although I'll tell you a tool after which you will not require all of this, but I still want you to know how to obtain equivalent resistance using first principles. It's cumbersome, but should be known, right? See, I can obtain I1, let's say, turns out to be some constant times I3 when I solve from this. And when I solve for I2, I2 turns out to be some C times I3, right? When I solve using these two equations, I1, let's say, turn out to be C1 times I3, and I2 turns out to be some C2 times I3. When I solve these equations, I'm not spending time on that. Okay, so I1 is C1 times I3, I3 into 4. I1 is C1 times I3, I2 would turn out to be C2 times I3. Do you realize that I3 will get cancelled? And you'll just get a number out of this? I3 will get cancelled from numerator and denominator, and you will just get a number out of this, which will give you the equivalent resistance across A and B. Yes or no? We'll save the calculations. We'll not bother about that, but just to tell you what needs to be done. Right? All's good? Huh? We can take the... I'll tell you. The third loop is this. For example, this outer loop. That's the same equation. When you add the equation for these two loops, you will get the equation for the third loop. That's not an independent loop. I'll explain. She's saying, this is one loop, this is another loop, and you could take any loop. There are no restrictions about which loop you take. You could apply KVL to this loop. When you apply KVL to this loop, actually you will not get an independent equation. That's the same as the two equations added. This loop equation and this loop equation, if you add, you will get the equation of this outer loop. KVL applied to this outer loop. This is what you will get. Right? So, it will not give me an independent equation. It will not give. So, you can't solve for I1, I2, I3 here. Why? Because this V is hypothetical. So, different V's will give me different I1, I2, I3. So, you can't have specific values of I1, I2, I3 anyways coming for you. Right? You will always be short in terms of number of equations that you have, because this is hypothetical V. And the equivalent resistance will not depend on what V is. It should be independent of V. Any battery connected, the resistance across A and B will be the same.